Alright, silly people, here's the situation. We have a particle in a box, and we're going to be looking specifically at a wave function, which is defined by, it's a time-independent wave function, where it's a constant to be determined in the region between over 2 and 0, so basically just the left half of the box, and it's 0 everywhere else. And we need to figure out what the constant is. We need to figure out how likely that we find it in the first um, energy eigenstate. So to normalize it, or I mean to find the constant, we normalize it. So we just integrate the wave function from over all space. Integrate the square modulus of the wave function over all space. And that turns out to be a squared dx from 0 to a over 2, and then integral with a over 2 to a, where you're just integrating 0. I'm just not going to integrate that because that's just going to end up being another constant. And so just this integral will evaluate to a over 2. That's pretty easy. And we have an a squared on there. We have to set it equal to 1, so that's going to tell us that a is equal to square root 2 over a. Easy enough. Then we can write the wave function again with this in mind. Hello. It'll be from 0 to a over 2. It's just the square root of 2 over a. And then 0 everywhere else. Right? Okay. And then to get the probability that we find it in the first energy state, we just have to find the constant C1 from the definition of the states of the particle of the box, with the general formula to find Cn being Cn equals root 2 over a times the integral from 0 to a sine n pi x over a times psi x0 dx, right? That's just a constant telling you how much, given a wave function, does any particular eigenstate contributes to the total wave function of the particle. So for C1, just plugging 1 into there, and our wave function, we'll have 2 factors of root 2 over a. We're only integrating from 0 to a over 2 because that's the only part where the wave function exists. We have sine pi x over a here, and that's it. That's what we're integrating. And that's not too bad of an integral either, so we'll just get a over pi minus, and it'll end up being cosine pi x over a, which we're evaluating from 0 to a over 2. And so those a's at the front cancel out actually, so you just have a minus 2 over pi out front there, and you get a nice little cosine of pi over 2 minus the cosine of 0. And then the cosine of pi over 2 is 0. Cosine of 0 is 1, so we just get a 2 over pi for that. Finally, using this formula up here, we can calculate the probability that we find it in the first energy state as being C1 squared, which is 4 over pi squared. And I didn't think to actually get a number for that, so about 0.4, so 40% chance you find it with the first energy, just for the wave function that is constant on the left side of the box. All right.